to tell you about Zerocash, Decentralized Anonymous Payments. I'm Eran Tromer, and this is joint work with my co-authors, Eli Ben-Sasson, Alessandro Chiesa, Christina Garman, Matt Green, Ian Myers, and Madras Virza. And as of a few minutes ago, you can read more about this project at zerocash-project.org, our website which went live just now, and it has the short and long versions of the paper along with other hints and Q&As. So, Zerocash. Zerocash is our answer to the problem of Bitcoin privacy. Now, Bitcoin, being a decentralized digital privacy, has this little problem that its coins are digital. They're just numbers representing digital signatures sitting in someone's mind. And numbers can be copied. So if I paid one merchant, I can take that same string, those same bits, and double spend them, send them to another merchant, and so on. That, of course, would completely devalue the currency. How do we do that? Well, the brilliant solution of Satoshi Nakamoto, whoever that may be, was to simply broadcast every transaction and summarize it in a blockchain. So whenever a new transaction takes place, it's recorded for everyone to see, and if there's an attempt to double spend a transaction, it can be immediately noticed. Of course, there's a lot of machinery, proofs of work, distributed protocols, and so on to make it work. But that's, for the remainder of this talk, just pretend that we have the ledger work and figure out what are the implications. So the first implication is privacy. We know that once all the transactions are broadcast, they can be analyzed. And there are several papers. There's a lot of ad hoc evidence that looking at the transaction graph can reveal a lot of information about what is going on and who is doing it. Now, of course, Bitcoin is pseudonymous, but most people use only one or very few pseudonyms. And once people know what your address is, what your pseudonym is, they can track your transactions. So if you're a consumer, then your friends, your neighbors, your coworkers, those who have ever seen your key can see what transactions you're making, what merchants you're paying, when, and what amounts. On the other side, if you're the merchant, then once your competitors know what your key is, they can track your cash flow, they can track your customers, a lot of valuable business information, and of course many other scenarios that are enabled by broadcasting transactions. Something that, strangely, none of us would be happy with other systems. None of us would post their credit card bills on the website. But somehow we are asked to be comfortable with broadcasting our transactions. So of course this has received some attention, and there's the idea of using mixes where we all send our money to someone and they redistribute it, and it's by going through that trusted central party, the history of the value is mixed and hopefully erased. But that requires trust in that central party. So Zerocoin, by some of my co-authors, Ian, Christina, and Matt, and also Avi Rubin, tackled this with a very nice, very sophisticated cryptographic approach. The idea is to create a decentralized system that does not require trust. Instead of a single party, we use cryptographic proofs to ensure that the mixing was done correctly. I think that's a beautiful idea, but it does have some constraints in performance and in functionality. So regarding performance, one problem is that those proofs that are required to ensure the correct operation of the mix are about 45 kilobytes per transaction at the level 128-bit security. They take about half a second to verify. Moreover, these mixes can only work on values of the same denomination. So you cannot split values. Of course, you can always send multiple coins
of the same denomination, but then you're leaking information about how much you're actually using the mix for. And when you draw money from the mix and pay someone, that transaction is a normal Bitcoin transaction. It is public and visible, so that information leaks. In particular, there's no way to just send information through the mix and have it appear somewhere anonymously. It all has to go to and from normal Bitcoin transactions. And also, disturbingly, this requires explicit operation. A user has to take his coins, load them into the laundry service, wash them clean, and then get them back. And the problem is that most users just wouldn't bother to do that, and the power of mixing comes with numbers. So we are not protecting the people who we would most like to protect, which are the casual users. Addressing the performance challenge of Zerocoin, there was an independent work called Pinocchio Coin that proposed to implement a variant of Zerocoin using zero-knowledge proof systems, using their Pinocchio system. So the idea is similar to the basic version of the scheme that I described next, but I will say that their system has a scalability problem in that the creation of proofs is inefficient. It grows linearly with the number of coins created so far throughout history. And it's still limited to being a single denomination. It still reveals the amount by going through plain Bitcoin, and reveals the destinations, requires explicit operation, and so on. And there are several other proposals. I won't go into these, but the bottom line is that none of these provides what we really want, which is a system that is efficient and transparent, fully preserves all aspects of privacy, is safe, and is on by default for all kinds of transactions. And that is what we aim to achieve. That is what we have achieved through the Zerocash system. Zerocash is a divisible anonymous payment system. I'll define this notion later on. But intuitively, what it is a privacy-preserving protocol, which is a digital currency that could operate independently, but is actually best seen as sitting on top of an existing non-private currency, like Bitcoin, or any other ledger-based currency in the spirit of Bitcoin. And it fixes all of the problems we saw before. It enables users to pay directly. And when one user pays another, all that shows up in the ledger is some pseudo-random numbers that reveal nothing. The transaction amounts can vary, and still the content of the ledger does not reveal the amount. And destinations can be fully anonymized in terms of who is sending and to whom. Moreover, Zerocash addresses the efficiency issues of Bitcoin and, of Zerocoin and Pinocchio Coin alike. The required cryptographic proofs are pretty small, 288 bytes at 128-bit security, much smaller than 45 kilobytes. They are very easy to verify in a few milliseconds. Creating such proofs is not a trivial affair, but it is doable. It takes under a minute. And it actually scales logarithmically in the number of coins. So under a minute, it supports 2 to the 64 coins. And if you need more than that, then in a minute and a few seconds, you can get twice that. So,
I'm sorry, say it one more time. What is it logarithmically? The creation time is logarithmically?
So the creation time increases by a small constant factor, say a few seconds, for every doubling of the number of supported coins.
Right, got it.
Now, the intuition that is strangely cut out by the slide is very interesting. The idea, in a nutshell, is there are values that are needed to verify the validity of transactions. Revealing those values will let us ensure the monetary invariance, but would violate privacy. But there's someone who already knows those values and can look at them without violating privacy, and that is the person who is making the payment that knows the value anyway. They know how much they're paying and to whom. So why don't we have the payer who issues the payment validate things by himself? He can look at the values, run whatever computation is needed on those values, and say, yes, I checked my own payment and it's legitimate. Well, that's not very convincing, right? Why would anyone trust me to verify my own coins when I could just be lying? But then there is a procedure there. There is some logical predicate that needs to be checked. So imagine if you had an accountant that you could invite over to your office, and they would look at your books and make sure that everything is correct, all the monetary invariants were fulfilled, and they would issue a statement saying, yes, that person who is trying to make the payment has that coin correctly generated. Well, that's kind of nice if you trust the accountant. But of course, in real life, we can't have that. So what we do instead is we create a virtual cryptographic accountant. We create a proof that is as convincing, perhaps more convincing, than a trusted accountant that carefully checked the books. And it can be efficiently verified and implies all the requisite properties for the currency to maintain its value. Now, before I proceed, I should have some warnings. I know that seeing these kind of things, my first instinct is to itch to code and see what happens and use it. But there are some things to be aware of. First, as always in all cryptographic constructions and all variants of Bitcoins, there are cryptographic assumptions. We're making assumptions about the behavior of SHA-256, comparable to ones used by Bitcoin. We are using elliptic curve cryptography and pairing-based cryptography. Pairing-based is very standard and accepted nowadays, but it's still a stronger assumption. And we're also using somewhat more exotic assumptions called the knowledge of exponent assumptions that are required for the underlying proof systems. These are relatively new. They have been out for a few years. They seem robust. I'm not aware of any attacks against them, but it's something to bear in mind. It's not as well established as vanilla elliptic curve crypto. Another practical concern is, in terms of efficiency, there is a big public parameter file that needs to be created and distributed. It's almost a gigabyte in size, and everyone who's going to make transaction needs a copy of it in order to create their proofs. Now, a gigabyte, in this day and age, it's practical. It's smaller than the blockchain. It's probably smaller than the smallest SD card you can find in a shop. But it's still awkward. The good news is that you only have to download it once. It's only created once in the lifetime of the system. But maybe for very small devices, it will be annoying. And on related note, creating that file, creating those public parameters, requires a trusted party. So it's only done once, but if that party is corrupted during that initial setup phase, they could forge coins, and we'll discuss that. So let's dive into the Zerocash scheme. So let's look at the Zerocash scheme, and let's start with a blank slate. Let's start with a very simple protocol and build up from there. And that protocol is by Sander and Tashma, and they had the following interesting idea. Suppose you want to distribute coins. What you could do is create coins in the following way. Every time you want to create a new coin, I pick a random serial number for that coin. I pick some commitment randomness, and I run a commit function, just a standard cryptographic commitment, to create a new value called a coin commitment. Now, this commitment has the property that just from looking at this value, you have no idea what the serial number is. It's hiding, and moreover, it's committing in the sense that if I'm asked to explain that commitment by showing the inputs, the SN and the R, I will not be able to find any other values except for the correct ones that I originally used. Now, in order to mint such a coin, I just create a transaction and broadcast it, saying that hereby spend, say, 1 Bitcoin, spend using the standard Bitcoin machinery of inputs, and I create a new coin commitment CM. I record this. Now I own a coin. Later, when I would like to use it, a bunch of these coins show up in the ledger, statement of this kind with the associated coin commitment value. And later, when I will eventually want to use it, so, well, if I didn't care about anonymity, I could just say, well, I'm using up some coin with a unique serial number. I expose the serial number, and now everybody can check that I haven't exposed the serial number before, so the coin is not double spent. And moreover, well, I show its CM and let everyone check that this CM is indeed in the list of previously published CMs. So that is sufficient to make sure that the only coins that are spent are the ones that were minted. But of course, it doesn't give any anonymity because when I spend, I reveal the serial number, and I reveal the CM, the coin commitment. And revealing the coin commitment lets everybody associate that spending with the original minting that declared that CM. So there is no anonymity whatsoever. And therefore, we need a different trick. And here it is. What we do is we take all of those coin commitments in the ledger that were created using these mint transactions. We create a Merkle tree over them by applying a collision-resistant hash function in a tree structure. There's a root. This is all public information. Everybody knows it. Everybody knows what the root is. And now I make the following statement in my spending transaction. I say, I'm using a coin with a unique serial number that I hereby expose. So the serial number now became public information. And I also claim that I know a coin commitment in the tree, and I know an R that matches N. But otherwise, I know some CM, such that SN and R map to CM, and CM is in the tree, but I don't show which one. And that would actually be an anonymized version. Now, what does it require to convince you of that proof? This small virtual accountant, this is the first example we see of that. It requires several properties. Well, first, it should really be a convincing proof. Let me relax that notion a little bit for efficiency reasons, and instead of a proof, I'll make it what cryptographers call an argument, which is a computationally sound proof. It's a proof that an infinitely powerful cheating prover might be able to subvert, but any efficient prover, any practical one, will never be able to falsify. So I want an argument for this statement. I want it to be non-interactive, so I can put it in the ledger, right? The proof systems can be interactive. That's not any good for a distributed system. We want it to be something we can just post on it as part of a posted transaction on the ledger and be done with it. We want it to be zero knowledge, in the sense that even though people are convinced that CM is in that tree, they have no idea which entry in that tree it is. It does not reveal any knowledge about the statement other than its truth. We want it to be what's called a proof of knowledge. And that means it's not just that there exists a coin commitment, but I know which one it is. And that's important to make sure that the security really goes through. And lastly, we want efficiency, succinctness. We want the proof to be small. We want it to be efficiently verifiable. So these are the proofs that, the properties that we need. It's, each one of these is necessary for the construction, and taken together they suffice. And taking this acronym, we call it a ZK-SNARK. That's the name of the cryptographic primitive that formally captures these properties. And ZK-SNARKs have a glorious history. let's start with recent history. These are not the first times they came up, but this is currently the most effective branch for constructively building them. So one kind of ZK-SNARK are what's called pre-processing ZK-SNARKs. Those are the ones that need that big public parameter file. And they're pretty new. The first one was proposed just a few years ago by Groth. Then there was a series of papers founding a theory of how to build them and what assumptions they can be constructed based on. And just the last couple of years, there's also been a flurry of activity on implementing them. Real working systems that create zero-knowledge SNARKs for very expressive classes of statements. In fact, all statements in the NP language, but otherwise all computations that can be done efficiently using even non-deterministic advice. And to give one example, so this paper called SNARKs for C showed a system that lets you verify any C program. It takes any C program and compiles it using a customized GCC compiler into one which doesn't just, so the final program output by the compiler doesn't just produce the output, but also produces a proof that the output is correct. The proof is less than 300 bytes long, it takes a few milliseconds to verify, and verification was demonstrated on a cell phone in a live demo on stage in Crypto 13, so it really works. Those are the systems that we build on here. These systems do have the drawback of having that trusted public parameters or system parameters generation, which we'd really like to get rid of. And in theory, we know how to do that using probabilistically checkable proofs. These do have a much longer history. So Mikali in '94, following the work of Kilian, first showed how to use PCPs to create what we can now call SNARKs. The PCPs themselves have hundreds of papers on their construction. And to date, most attention has been mostly on very theoretical perspectives. Polynomial time existence, asymptotic properties. There's one recent paper that tackles more practical efficiency, and we believe that within the close future, we will see these coming to fruition and providing an alternative that removes the trust problem. Now, you may notice that several of these papers have author names that are familiar from the first slide, despite my botching of its presentation. And that's not a coincidence. In fact, we have a large project called SCIP Lab for succinct computational integrity and privacy research, collaboration of Technion, MIT, and Tel Aviv University. And part of the slides that cut off says that if you go to skipper-lab.org, you can see all of these papers and read more about the underlying technique. And the reason I'm emphasizing this is that these underlying techniques are very general, as suggested by SNARKs for C, and we'll be discussing some other potential applications for them beyond Zerocash. Specifically, the SNARK that we used in Zerocash is from this paper. This paper actually shows the high-level functionality using a virtual processor, running machine code and verifying it. What we did is take that, the underlying SNARK, which is the latest and greatest, and I'll show you shortly what we did with it. So actually, questions so far about SNARKs before we go back to Zerocash? Yep.
So the parameter generation, if it's deterministic from the source code of the C program that's running on the SNARK generator? Or is there, so like, if we both, so I have to trust that the parameters were generated correctly. If I had the source code, could I verify that I came up with the same parameter?
So the question was whether the parameter generation is deterministic and therefore verifiable. Unfortunately, it's not. It's randomized, and actually that's why it's trusted. No one must know the randomness.
I mean, is that, are you going to have a multi-party generation of that? And can you like put 20 parties in such that and only one is needed to be
indeed, one way to do that would be to have a multi-party computation that can be done using protocols that for security it suffices that a single person is honest. We'll get there later in the talk, but these are great questions, and indeed, something like this should be done using the current technology.
And could you just repeat again, this PCP-based SNARKs should be able to remove the need for that 1 gigabyte file, but not necessarily soon enough such that you're going to use it immediately, is that right?
So the PCB-based SNARKs will eliminate that public parameters file. There will not be any big static file or any key whatsoever, just a description of a suitable field and the code itself.
But I mean, apparently it's not quite polished enough so that you could use it immediately in Zerocash. Is that correct?
It's not ready for immediate deployment, no. Okay, so going back to Zerocash. So we started with some very modest requirements that look like this, just a single commitment. But I just told you that we can create zero knowledge proofs for arbitrary NP languages, for arbitrary C programs. So let's get greedy. Let's start doing more. Let's flex the muscles of the ZK-SNARK to make the virtual accountant work harder and check more sophisticated properties and therefore give us more functionality. We're going to add values to coin. Every coin will have a value denoted in Satoshi or whatever your favorite currency is. Let's call it V. And when you create a coin, you would now need to declare that value. And that value will go into the commitment, producing the coin commitment. Now, another change that we'll have to do, and you'll see momentarily why, is instead of having the serial number go straight into that commitment, we're now going to have another intermediate commitment. So the serial number is committed into a value K using commitment randomness R double prime. That gets committed into the final CM using a commitment randomness R prime. Now, to mint a coin, to convince you that I indeed correctly created such a coin with the right value, I just reveal the value, and I reveal this intermediate commitment K and the commitment randomness R prime, and I say, look, here's a CM, and if you just do this part of the computation, you see that the V, K, and R prime that I gave you are consistent, so you can believe me that this CM is a commitment to stuff that contains the right value. Therefore, I can now spend, burn, consume V bitcoins and V satoshis, and in exchange get CM that captures a Zerocash coin with the same value V. So there's a one-to-one conversion rate between the underlying Satoshi Bitcoin currency and this value V. Okay. So now how do I spend this? To spend this, well, I could just reveal everything like before, but that would not be anonymous. I would like to do it in an anonymized way. So what I do is I'll publish in the ledger a transaction saying that I'm using GAP, I'm spending some Zerocash coin with value V and a unique serial number that I now reveal. And moreover, well, I want to say that these V and serial number are somehow related to a CM that appears in the ledger as having been minted. And the way I do this is by convincing you that I know R prime and R double prime. Please ignore these two, they're a mistake. So I know R prime and R double prime. That suffices to convince you that CM indeed contained V, so it's the right value, and SN that that has not appeared before, so it's not double spent. and it doesn't reveal anything else by virtue of being zero knowledge. Again, I'm using a zero knowledge SNARK for that. Moving on, I would like to add additional functionality, and that is adding direct anonymous payments. So now that I have coins of variable denomination, and I can spend them myself, I would also like to be able to directly send these coins to someone else so they can spend it. And that would let me create a whole currency that is completely opaque to people who are not part of the respective transactions. To do that, I further complicate the structure of the coin. It has grown, and it now contains what we just saw before, this commitment to create a CN, and preliminary commitment to create K. There's a value V. But now there are other things going into this commitment. First, there's the address of the destination. Now, in order to have an address, you need to create one. So we introduce a new algorithm for creating addresses. The payee creates a public key and a secret key. They publish it, and in order to create a valid coin, I would need to have the payee's public key be part of the inner commitment. Moreover, the serial number no longer goes straight into that. And the reason for that is if the serial number was known to the payer, then the payer could cause damage. The payer could send the coin to the payee and then reveal the serial number before the payee had a chance to claim that coin, thereby invalidating the payment. To prevent that, we must somehow tweak things so the payer who sends the coin does not know the serial number of that coin. The way that's done is by making the serial number be generated by a pseudo-random function by the secret key of the payee. Pseudo-random function applied to what? Well, to some additional serial number randomness, and that is also made part of the commitment. So we still have the CM and SN, just like in the very simplest scheme, but there's a whole lot of internal values, randomness, commitments, keys, leading to them. And it does have just the right properties we need. Some of it can be readily verified. For example, minting is just as before. I reveal just enough values to make sure that I minted the correct V without revealing what I shouldn't. As for actually sending things so they can be used, now here it's a bit tricky because we have two persons. The payer knows these secret values. The payee knows this value. None of them by themselves can compute all values, and in particular the serial number. And that's actually as it should be. The payee shouldn't be able to claim a coin until it's received it. So there needs to be an explicit protocol for sending a coin to the payee, and that's done by creating a coin with the public address of the payee, and then sending all of these secret values, V, rho, R prime, R double prime, to the payee. And then the payee will have all of these values, also his own secret key, therefore he can compute the serial number, and then he knows everything, and he can produce zero knowledge proofs and spend coins analogously to what we had before introducing direct payments. Now, there's just a question of how do we send those secret values to the payee, and there are two options. You can either send them out of band. If you have their public key, just send it by whatever channel you have. Alternatively, as we described in the paper, we can bake in a public key machinery into the very currency, so that you will know when part of the address of the payee will contain the public key to which you can encrypt those secret values. If you know that the payee's public key, you can send the information, the payee can accept the coin. Okay, so now we've seen the basic structure of a coin, but we haven't seen how other things are done. How do we combine coins? How do we split coins? How do we crucially go back from Zerocash coins into some mixture of Zerocash coins and public coins, transaction fees, and so on. And all of these are captured by a single operation that we call the pour operation. It's a single kind of transaction that provides a very general form that includes all of the specific operations I mentioned. And this general form is consuming 2 old Zerocash coins, marking them invalid, creating 2 new Zerocash coins with fresh serial numbers, fresh coin commitments, and so on. And also releasing some public value back into Bitcoin currency. Now, in order to create such a transaction, the holder of the 2 coins has to present his 2 fresh, unspent Zerocash coins and the corresponding secret keys, specifying how he wants this, the value of those 2 coins to be split among the 2 new Zerocash coins and how much to be released into Bitcoin outputs, and moreover, the addresses to which those fresh Zero coins should be sent, which could be his own or someone else's. Now, the pour operation works for a while. This is the heavy part of the computation. It takes on the order of a minute on a modern desktop. And it outputs a proof attesting that the old coins were valid in the same sense that we had earlier by showing the knowledge of the internal values that fulfill those graphs we had before, which represent a predicate on the validity of coins. Moreover, those SNARKs capture the fact that the values of the old coins and equal the values of the new coins in total plus the public value. So put otherwise, no new money was created. And moreover, it has to verify that the old coins were unspent to prevent double spending. In addition, there's a whole bunch of things outside this SNARK proof that go along, like the serial numbers of the old coins, the signatures on the destination of the public value if it's sent to some specific Bitcoin address and so forth. I'm afraid I won't have time to go into all these details. The paper is very explicit about them. I have to refer you there. Verifying this transaction, as you'd expect, verifies the zero knowledge proofs and then checks the consistency of all the other values included in it. But you know what? Let me actually show you the transaction. I won't read out all of the details, but we can get a feel for what's going on, both qualitatively and quantitatively. So this is an example of the content of an actual Zerocash transaction. It's about 1 kilobyte in size. It includes the Merkle root capturing the set of all coins created so far. Here are the serial numbers of the coins that were consumed, the 2 old input coins. Here are the coin commitments of the newly created coins. You'll note that this public is value. Serial numbers are just some random value that we're seeing for the first time. These are just some outputs of commitments. So far, intuitively, we haven't revealed anything, right? Here we do reveal something. We reveal the public value. That is that the fraction of the input value from the 2 input Zerocash coins that is revealed as Bitcoins. This reveals information, but of course this information has to be public. It makes it into the Bitcoin ledger. If the person who created the transaction didn't want it to be public, he wouldn't have made it so. So it's fine to have this information here. Then we have some more random looking information, but this actually is important. This is the destination of that public address, sorry, of that public value. The payer here wants to send 42 Satoshis to this Bitcoin address. So again, it's public, it reveals something, but by choice, we haven't violated anonymity. Then there's a bunch of strange things that are related to non-malleability. We won't get into that, but please believe me that they're all random looking and do not reveal anything about the transactions innards. These are two ciphertexts. If you use that option of having the caked-in public key infrastructure for sending those secret values needed to receive transactions, this is where you put them. If you don't want to use that option and have some external out-of-band channel, you can just drop these fields. And finally, the SNARK proof. So this is the actual proof attesting to some fairly complicated statement about the validity of the altcoins. And as you can see, it's a few hundred bytes in size. So all of this, taking a step back, all of this is a specific scheme. It's the best scheme we could come up with, but it's an instance of a more general idea. And that general idea is that of decentralized anonymous payment systems, which are the way that we propose to formally capture the functionality that we require. So I'll be very informal about the algorithms that we used and who does what, and actually that reflects the attempt to show you the interesting bits without getting bogged down in formalities. But in the paper, you can see a formal definition showing the algorithm setup that creates those public system parameters, the algorithm create address, the algorithm mint and its inputs and outputs, the algorithm pour and its many inputs and outputs, verify transaction, which does exactly what needs to be done in order to make sure that a mint or a pour transaction that appears in the ledger is legitimate by checking the SNARK proof and so on. And an algorithm receive, which is what inspects the ledger looking for transactions intended for me and extracts the requisite values from them so I can use these coins. The definition of decentralized anonymous payment systems defines these algorithms and how to use them, and then defines the security. There are three security properties here. One is anonymity, captured by ledger indistinguishability, which is a technical definition expressing a very powerful fact that nothing in the ledger reveals anything except for the public information. As I pointed out earlier in the transaction description. And this strong privacy property holds even against an adversary that can choose which transactions are to be done. They can manipulate parties into making any transactions that he wants. They can do transactions by himself, and yet he reveals nothing beside what is inevitable, just from the interface with the underlying currency, the public one. The balance property says that the monetary invariant is maintained. So no one can ever own more money than he received from others or minted from the underlying bitcoins by consuming them. And transaction non-malleability is a technical but important property saying that a man-in-the-middle attacker can't intercept a transaction along its way to the ledger and corrupt it to change its value. For example, to have the public value sent to the attacker instead of its rightful destination. That, as you saw earlier, requires some extra machinery in the transaction. So we define this as the primitive. We described the scheme, and then we went ahead and instantiated and implemented it. We made concrete choices for all of the parameters and the underlying cryptographic primitives. We chose the best zero-knowledge SNARK available, and then we expressed our statement, the one to be proven by the SNARK, in the best way we could by speaking in the native language of the SNARKs, so to speak, which are roughly arithmetic circuits, and then hand coding the constraints, logical constraints required to check transactions in that low-level language. It was significant work, but it's part of the key to vast improvements in performance. Without this, had we gone through the generic C compiler, things would have been orders of magnitude slower. Now, this is all wrapped in lib Zerocash, which is a library that creates the decentralized anonymous payments interface and abstracts away all of the underlying cryptography. And then we have Bitcoin de-adaptation that uses lib Zerocash to actually integrate and interface this with the Bitcoin protocol, both in the sense of the protocol messages and in the sense of the monetary integration with the currency. To make sure that it indeed works and that the delays in verifying transactions and sending them are manageable and don't create any bottlenecks in the distributed ledger protocol, we actually went ahead and simulated the operation of a Zerocash augmented Bitcoin system on a scale comparable to the whole of Bitcoin. So roughly a third of the Bitcoin, according to published estimates. We got a whole bunch of EC2 virtual machines, each running several simulated nodes. We ran it for a while, and it performs nicely and as expected. And to be concrete, so here are the most interesting numbers from the profiling data. So the trusted setup takes under 2 minutes, creates under a gigabyte of a proving key. Minting is very fast, creates very small transactions, basically free. Pouring coins, that's the heavier part. That's the thing that will be done commonly and is most resource consuming. Well, it uses that big proving key, and then it runs for about a minute on a modern quad-core desktop. On a smaller device, it would be less. It will improve with time. Usual trade-offs.
How long did you say it ran for?
About a minute, 46 seconds on.
I thought you said 10. Sorry.
Okay. So you'll see different benchmarks in the paper for different processors and different levels of parallelism. It's on the order of minutes on any decent desktop. The transactions are about 1 kilobyte in size. The actual SNARK proof is about 1/4 of that, and the rest, as we saw, are various cryptographic fields, some of which are optional, so you can significantly reduce this if you wish. Verifying transactions takes under 9 milliseconds, and receiving takes under 2 milliseconds to check a transaction and extract the secret values if they are addressed to you. So I guess the sport transaction is probably the most bothersome aspect. But then if you remember that even today Bitcoin transactions take on the order of many minutes to go through, then it looks like this order of magnitude is acceptable. We'll certainly try to improve it, but it seems already practical. In terms of integration, and I think I should be going fast here, there are several ways to go about actually using Zerocash. One is to consider it an independent currency, sitting on top of some ledger, perhaps provided by some other currency using the standard techniques, perhaps its own. But I think a more attractive option is a hybrid system that allows for a smooth transition between public and anonymous values, just like we described so far. Minting consumes a public Bitcoin and creates an anonymized Zerocash coin, and when you pour, you can convert some of your Zerocash coins back into public Bitcoins. And it falls very nicely into the framework of Bitcoin's inputs and outputs. In the generalized scheme, you can have a transaction in the Bitcoin style, in the Bitcoin sense, where every input in the transaction can be, as usual in Bitcoin, a pointer to the output of a previous transaction. Or it can be a Zerocash pour transaction that released some Zerocash coins. That would be considered an input into the Bitcoin transaction, right? Some new value appeared, it can be used up. And then on the output of the Bitcoin transaction, well, Bitcoin transactions can, as usual, just present an amount and the destination public address script to be consumed by others. But the output can also be a Zerocoin mint transaction that takes that leftover value and converts it into Zerocash. So the input of one is the output of the other, and vice versa. Therefore, you can smoothly transition back and forth according to what your requirements or merchants or regulators says. And we'll get to regulators later. Now, the invariants maintains are the one you would want. You can imagine what they are, so let me skip forward. Now, the issue of trusted setup. I know that many worry about it, and rightly so. Recent revelations have certainly been keeping us on our toes, and we do have the need for a trusted party in the current implementation. It's generated once, but if it's compromised during that time, if at the dawn of the system where that public parameter file is created, the creation is compromised and that secret randomness leaks, then the attacker who knows that randomness can later forge coins. Well, the good news is that after transaction is done, there is no longer any trusted party. So you just, of course, need to believe the underlying cryptographic assumptions, but no one has any advantage. And moreover, anonymity is unconditional. So some of the agencies who are popularly perceived to have taken special interest in breaking anonymity would be disappointed to find out that even if they completely compromise the creation of those public parameters, they would still learn nothing about the transactions that are going on because all they would see is still pseudo-random values. There aren't any trapdoors in there. They could, however, find alternative funding sources. Now, there is a practical question to have. Before anyone can use this, then we, as researchers, as the community, as prospective users, as industry, we need to figure out a reasonable, trustworthy protocol for running that setup algorithm. It can be multi-party computation. It can be a big committee of wise old men trusted by everyone. It can be something physical, and I'm sure that at the end of the game, we'll have a lot of fun crushing that computer with big hammers and flamethrowers to make sure that no randomness leaks out. There will be some pyrotechnics there, and we need to find just the right protocol and the right people involved and the right physical setup. So most of us will be convinced, and I'm eager to hear your suggestions or fears about what that should look like. It will be a once-in-a-lifetime party. This is your chance. Alternatively, just wait until the PCP-based ZK-SNARKs that do not require this trusted preprocessing show up, and then there goes the firework. Well, you could compare the trust assumptions to prior works. let's skip this in the interest of time and get right back to the conclusions and the discussions of the road ahead. So I gave you a taste of Zerocash. I hope that I've conveyed why it's necessary, why it works, and why it's exciting that it works. The underlying techniques are extremely powerful, and they raise the prospect of doing more. Why stop at that picture with 2 commitments and a pseudo-random function and a bunch of random values? We can do so much more once we can take arbitrary NP statements or zero knowledge proofs and embed them into our very currency. So, for example, maybe we can take some policies, our favorite policies, whatever they are, and instead of requiring people to just compromise their anonymity, compromise their privacy and reveal transactions in order for the transactions to be verified, maybe we can just bake in the right policies and regulations. For example, enforcing cryptographically that the citizen will be able to make transactions only while paying the correct taxes in a way that just works without revealing the transactions unnecessarily, without the opportunity of corrupt tax employees making favors or abusing information. We could just, if we can just express the right predicate to be fulfilled, we can bake that into that zero knowledge statement that kept growing throughout the slide as just yet another condition. But what are these predicates? What are the policies and regulations that we'd like to enforce? And are they of the right syntactic form to be an NP statement? That is a question that I pose to you. Moreover, why stop there? We have such a tool. It found use in protecting privacy, but it can do so much more. One idea that came up that we've been discussing for a while is blockchain compression. The zero knowledge SNARKs that we use are zero knowledge. That's the main property that we used for anonymity, but they're also succinct. That's what we use for performance. And they're so succinct that they could prove something about the whole blockchain, gigabytes and gigabytes of data, and summarize it into a few hundred bytes. For example, I can prove that in plain Bitcoin, I can prove that the transaction is unspent and have you verify that in a few milliseconds without scanning the whole blockchain. Or I could prove that a transaction was correctly created by a valid chain of transactions leading back to a minting of a coin. And normally that would require unraveling the whole history, but actually I can summarize that whole history into a few hundred bytes. And then clients, restricted clients, could verify these, could verify that the payments that they receive is legitimate without having a copy of the blockchain and without trusting external servers or hoping that the latest version of their software will have some hard-coded block that's sufficiently recent. Another prospect is about the power of the scripting language, the plain Bitcoin scripting language or the ambitious and powerful version of Ethereum. We would like to have Turing-complete scripting languages that express complicated contracts and conditions. We have so many potential applications for this. But there is the burden of actually conducting the computation. And a Turing-complete language can run for awkwardly long without us even knowing in advance for how long. But there's someone who wants to run the computation in order to receive the payment, and they would presumably run the computation by themselves just to make sure that they got the money. So why don't they just summarize it for us into a few hundred bytes, and we can all enjoy the benefit of computation done once. And even if it involved very long loops, even if it consumed a lot of memory, it can be summarized succinctly and checked by everyone in a few milliseconds. Additional applications are proof of reserve, showing how much money I have at my disposal without revealing my coins and how my wallets and how my balance is split between these wallets. And many other ideas came up. So we've discussed SNARKs in the application to Zerocoin on a number of occasions before, even though this is our first written publication on it. But every time we did, the Bitcoin mailing lists and forums were filled with fascinating, intriguing discussions for potential applications. I couldn't attempt to summarize them all, but I would like to hear about them all and to help you implement the ones that work out. And last, I should mention that SNARKs are not just for Zerocoin. There are many prospective and potential applications. Outsourcing information to an entrusted cloud, trusting city-at-home style computations, proving the provenance of data, enforcing consistency in massively multiplayer online games without loading the server, proving provenance under various regulations, and much more. We are aggressively seeking such applications. Zerocash is our first and greatest so far, but I hope for many more. And the SCIP Lab project is pursuing these along with a new commercial ventures called Tegos Technology that seeks commercial opportunities for these proof systems. If you have ideas within or beyond the realm of Bitcoin, we would like to help you make them possible. So I'll take questions at this point. Yes?
Zerocash that you use for your EC2 S implementation, is that up on some repo that people can look at and work with?
So Zerocash is under development. We are still stabilizing and testing. We would like to be as confident as we can before releasing such code upon the world where it could be hastily used. What we will open source soon is the first component, which is an underlying library called libsnark, which provides the basic cryptographic system. That can be used to create proofs for arbitrary statements, and we will follow on with the further releases.
How early? Next week?
Actually, libsnark is expected within the next few days.
So, since you said you could implement your system on top of something like the Bitcoin blockchain, what's your incentivization to actually run this? Like the verification or the creation of these proofs, are you going to use block rewards like Seigniorage that Bitcoin does? Or if I'm a user, why would I want to mine or whatever you want to call it?
So you raised the excellent question of mining incentives. So one lucrative, simple way to do it is to piggyback on an existing blockchain that has its own mining incentives. But in general, it's the same question as for other altcoins. And it has been extensively studied. We are still evaluating the best option for Zerocoin.
So one of the applications I'm looking at is data provenance. You talked about Tegos Technologies. What is Tegos Technologies? What would they do? How would they help someone like me looking to put together an application of that size?
So the CEO of Tegos, that's Josh Kanner, is sitting right next to you. So you can ask him all about it.
Yeah, great talk. Thanks for presenting a lot of the intuition. Can you recap again on the POR? Is POR kind of like sending or what's the...
So POR encapsulates a number of functions. It includes the sending your Zerocash coins to someone else. It includes making change, say taking one coin and splitting it into two, or conversely merging two coins into one, so you can send it in a single transaction. And it just, for convenience and generality, we capture this using a single general transaction type. Curiously, because it's merged into a single general transaction types, when it happens, then people who look at the ledger have no idea which one it was. So just taking two Satoshis and merging them into one locally looks the same as paying 1 billion Satoshis to someone across the internet. It just pseudo-random record in the ledger.
If you pursued the implementation where you sort of piggybacked on the existing Bitcoin implementation, would the value of a unit in Zerocash be pegged to the value of Bitcoin, or would
So if things are implemented the way I described, then yes, you have you have precise one-to-one pegging simply because you can freely convert one to the other. Alternative mechanisms using altcoin mechanisms would have different dynamics, of course.
There's a difference between sort of two-way pegging where you have a new currency running a nominate versus where, say, you have a hypothetical order you declare we modify the Bitcoin code, insert all these bits. If you did the latter, you'd end up with that. If you did two-way pegging, you could also end up with it, but it's somewhat increasing technical overhead.
Right.
Will libsnark be free software? Will it be sort of unencumbered? I ask because I know that there's like Pinocchio and the Skipper group are sort of competing implementations of snarks. I'm more familiar with Pinocchio, but the Bitcoin developers, I think I rightly said that it's kind of a non-starter because the kind of release conditions of it say that you can't use it for applications resembling Bitcoin. So I wonder if libsnark's going to be different.
We are well aware and supportive of the Bitcoin's community preferences for liberal open source licenses and intend to follow it.
So on that same topic then about your source code, have you investigated the export information? Like, anybody, no government agencies pinged you about cryptography exports? Or I don't know, maybe you're familiar with this. Like, it's got to be a topic among cryptographers about export stuff.
So export controls are a complicated affair. I am not a lawyer, usual disclaimers. It has been a while since a cryptographer, especially academic researcher cryptographer, or I should qualify that more precisely. It has been a long while since academic cryptographers encountered any problem of that sort. It would be very amusing if that monster rears its head again. It would be especially amusing given that this is an international collaboration. I'd like to see them try.
I have a bunch of questions. I don't want to stop until you can
do it offline?
Well, I don't know. Okay, so it seems you talked about Bitcoin there several times, but I guess, you've talked about also releasing this altcoin. So I guess a lot of times when you're talking about Bitcoin, you're meaning your non-anonymous currency. So
Right.
anyway, I guess maybe there should be another name for that if you're using Zerocash as the anonymous currency or the anonymous version. And I guess kind of a separate question is how separate are they? I'm guessing they would be, let's say you're spending Zerocash. I mean, you could spend either one, is that right? I mean, maybe I'm a little bit fuzzy here. I mean, is there so let's say you build, you're talking about building an altcoin, right? Using the Bitcoin library. And so I think that your vision is two currencies, an anonymous and a non-anonymous currency. Is that right?
So let me answer first your first question. I use Bitcoin for concreteness, but as I said in an early slides, all we use is the Bitcoin-like ledger structure and transaction structure. In particular, all I said applies to almost any altcoin currently in existence. As for which currency to use, so if we go for the hybrid approach, we end up with a free one-to-one conversion bidirectionally between the public Bitcoin or other altcoin currencies and the privacy-preserving anonymized Zerocash ones. Which one will you use? Well, you're at liberty to convert from one to the other, so this will be a practical affair. If you're paying a legacy merchant that only accepts old Bitcoins, you will have to use your stash of Bitcoins or convert your Zerocash coins into Bitcoins. If you're using a modern, privacy-aware merchant, you do the other thing. You could be maybe under some compulsion or regulation to use one or the other. It becomes another degree of freedom, but what I hope to see is people protecting their own privacy by using the privacy-preserving one as a matter of course.
You mentioned government being able to regulate the taxing of transactions, and to my mind, it seems like that would only work if we had a world government or a government that agreed on international law and how that was going to be done, because there's no possibility of knowing where the transactions are between citizens of which country.
Right. So the question is, if you want to apply regulation and it's at the national level, how can you enforce that on a system that is inherently international? Well, you could couple this into national PKI schemes. For example, you could have smart cards containing certificates specific to citizens, like there already are in various countries, in ID cards, passports, and so on. That will identify you as a citizen of country X. And the predicate enforced by the Zerocash successor would say that if that every wallet should have a certificate properly signed by a national authority in order to be accepted by designated merchants, or in order to make it past choke points in the economy, like conversions into local currency. You can imagine a lot of integration going through PKI and certificate infrastructure to express external physical world or national legal world properties within the cryptographic predicate.
Would users of a Zerocash like system, just for anonymity, going back from an ambitious and interesting question to a very basic and mechanical methodology. So if I understand things right, the pour operation is kind of at the heart of things here, where a user does a pour and it doesn't reveal anything about to whom or from or whether things are being merged or paid, but it's visible that something's happening, right, on the network. Would users have to be careful about not falling into certain habits of timing, like immediately upon having received, somebody pours somewhere else and somebody pours here, and an agency watching the network draws inferences about, oh, that looks like it might have been a transaction between those two parties?
That's a great question. So the question was whether timing analysis and traffic analysis are still possible. If you see correlations between transactions, it may imply something. So in particular, if you only had 3 people in the universe and you see a transaction, a broadcast on the distributed ledger by Alice, and a second later you see another transaction broadcast on the ledger by Bob, you can be pretty confident that it was just Alice that sent something to Bob and Bob received it and did something about it. That's true. That is inevitable for the current ledger systems. And the way you would fight it is through generic countermeasures against such traffic analysis, for example, the Tor network. So 288 bytes is the size of the SNARK proof at 128 byte security level for best proofs to date, the paper I pointed out earlier. The rest of the overhead is outside of the SNARK proof itself, but rather the serial numbers and the destination address for the public value, the various fields I showed in the big table. And actually, just by looking at the table and counting characters, or better yet, by looking at the paper that has an explicit figure showing precisely this, you can see where the costs lie and which optional components can be turned off if you are very demanding about transaction sizes.
Okay. So you had a figure, your last table, it might be still there if you, I guess we're not seeing it there, but you talked about this long list of
This one?
fun.
Oh, this one.
Yes, of fun things there. Cheap verification, Turing complete scripts, blockchain compression. So I'm just curious, how close to being available those are. For example, the blockchain. I'm slightly fuzzy about this blockchain compression. One of the big problems in all cryptocurrencies is the requirement that every node process every transaction. And I still haven't quite figured out. My understanding was that there's a way to use SCIP to solve that problem. Is that correct?
Just one guy will do the computation and then just publish the SNARK.
Yeah, that's my understanding. And so yeah, rather than every node doing every node repeating the transactions, one guy would do the transaction, he'd publish his zero knowledge proof that he had done it. The other guys could just verify the proof rather than repeating the transactions.
So there are different ways to implement it with different trade-offs. But you're right. There are variants where nobody ever looks back at the history, and actually every transaction has just a local proof generation associated with it that basically increments an incremental proof that summarizes the whole state of the world to date. So in those variants, nobody ever needs to see the whole blockchain.
Okay, so I guess a little bit. So these things that you listed there, the blockchain compression and the Turing complete scripts, I guess is there a lot of work? Maybe this is a very open question, but I'm just wondering, is it like 2 months of your PhD guy's work, or is it like a year? Or I don't know how big of a deal it is to do some of those things that you described right there.
So there's a combination of factors here. One is just figuring out what's really needed, what are the problems that need solving. Then you figure out whether they can be really expressed as formal statements of the kind that can be proved by SNARKs. And then you figure out whether the state of the art in SNARK technology can support them. So, for example, blockchain compression requires SNARKs that look at themselves at at least the simple version of blockchain compression requires SNARKs that themselves look at the whole blockchain and summarize it. So, given the current overhead of SNARKs, this would be extremely expensive. Now, right now in the lab, we're building a more powerful version of the SNARKs called proof-carrying data that give you that incremental property. Using this, you could imagine doing blockchain compression much more feasibly. So most of these applications, I would say, will be at the very least pushing the state of the art in SNARK technology. But the good news is that once we know what they are, once we figure out what are the really exciting systems to build, we can also tailor the SNARKs and find the application-specific shortcuts that make things more efficient, as we did, for example, with Zerocash.
Could you briefly go back to the slide before this and one you skipped over about this
Yeah.
one? Just quickly describe it.
Okay. This is a brief discussion of trust assumptions. I'm comparing here three systems. The simplest mixing we described at the very beginning of the talk, where you trust someone. There's an operator that you have to trust. You have to trust them for every transaction. They can't forge coins, right? Because they're still subject to the Bitcoin rules. But they can steal your coins. They can trace you and break anonymity. And of course, denial of service applies. Then there's coin join using multi-signatures, using the current Bitcoin functionality. Very interesting idea, very elegant, especially since it's doable without extensions and despite the current limitations of script. But you still have the problem of having to trust participants for every transaction, and anonymity can be broken, and denial of service still applies. With Zerocash, the current one, you only have to trust the setup. If the setup is corrupted, then forgery is possible. This is the only of these four where forgery is possible, but only that extreme case. And with the PCP-based ZK-SNARKs that are down the road, we'll be achieving all of these properties. So you don't have to trust anyone, and therefore there are no failure modes due to trust. And it's also, it doesn't have any centralized system that's resilient to denial of service.
If you're familiar with them, would you care to contrast Zerocash with any of the altcoins that seem to be positioning themselves as privacy technologies? The two that come to mind the most are Dogecoin and something that I think is called Monero, which is based on something I've heard called Cryptographic. I don't know if you're familiar with one or both.
Yeah, so I think there are at least half a dozen emerging altcoins that claim to provide privacy features. I looked at some of them, and one troubling thing is that it was hard to figure out what they do exactly.
Yeah, it can be a problem. Yeah.
That is definitely a bad sign. And, we went through a lot of length to publish very detailed specification and detailed analysis, formal definitions and formal proofs. I would not trust any system that doesn't do it.
You were a little fast when you were talking about how the pair all of a sudden no longer knows the serial number. Can we take a quick look?
Yeah, okay, let's go back. So the question was how the pair knows the serial number in our latest and greatest key, which is this one.
The one where it was a red.
This one?
Yeah, that's right.
Okay, so the pair doesn't know the serial number. That's actually a goal of this design. We added some extra mechanisms here, specifically the pseudo-random function, the derivation of the serial number from some value.
So what's the sentence now when they're sending? What's the sentence that I say when I'm sending? Because before I used to say that I have a serial number.
Okay, so in order to send the coin, you just send those internal values, all the hidden values here. You send them to the payee. Now they have full control over the coin, and they can prove any statement, any true statement about it. And in particular, they can prove a statement of the flavor we had before. Let me go back. That they're talking about some CM that is in the Merkle tree, and they can reveal the SN, and they can reveal those internal values that now they know, and prove in zero knowledge that all of these are consistent, but according to the new coin structure. So this is what the recipient would do after they know all of the values, and that would be included in the poor transaction. This is the part of the poor transaction that convinces the verified transaction checker that the poor transaction consumed a valid coin owned by the recipient.
Okay, if I'm paying you though, I have to know the coin that I'm paying you with, right?
But you don't know everything about it. You know some of its values, but not all of them. Some are only meant for me to know. So if you created a coin that's addressed to me, then you don't know everything there is to know about it. It is a bit surprising.
Wait, but then once I send it to you, you know all the values.
Right.
So when you send it to someone else.
Excellent. So I can't send it directly to someone else because it really is addressed to me. See, it has my public key as part of the commitment. So what I would do in order to send it to someone else is to use the pool procedure to consume this coin and create a new one with the same value.
And you don't know the serial number.
Right, and I wouldn't know the serial number of the new coin addressed to the third party.
So when you say that if the setup is not trustworthy, then what can happen is the mean setup person can forge coins. But at the same time, in the concrete implementation, I know that this technique is not tethered to Bitcoin, but if we imagine the implementation that you described, where the construction of coins is linked to consuming Bitcoin and sort of redemption of coins is back into Bitcoin, is that a fair characterization?
I'm sorry, I didn't get the question. Can you repeat the last part, please?
So normally, when things work, nobody's cheating. To construct the zero coin in the concrete implementation you've been describing, you consume Bitcoins to construct zero coins, and then you can work in the zero coin economy, and then eventually, if you want out, you can redeem back into the zero coin economy, into the Bitcoin economy, excuse me. So I'm wondering, what would happen? Suppose we have Alice and Bob and a merchant, and Alice was the trusted setup party who was untrustworthy. And both Alice and Bob have one Bitcoin turned into zero coins, and so they spend their two zero coins to the merchant. But then Alice makes up a third zero coin. She forges one and spends that two, and then the merchant wants Bitcoin back. Is what's going to happen? The third one is going to fail, or?
Excellent question. So basically, you're asking a deep question about if we do this integration, this means that you can create Bitcoins by consuming Zerocash coins. So if Zerocash fails, then Bitcoin goes down with it. Because you can now create fake Bitcoins by first corrupting Zerocash and then converting those fake Zerocash coins into Bitcoin. So there are different ways to go about it. One is to create a currency where this is an acceptable risk. It may not, at least initially, be the Bitcoin, but probably some altcoin. Alternatively, you could set up an escrow pool, a backing pool for the currency. And you would know that every Bitcoin converted into Zerocash isn't burnt, but rather sent to some escrow pool holder, or perhaps virtually so using a cryptographic mechanism. And then when you convert Zerocash back into Bitcoin, you go into that pool and extract the corresponding Bitcoins through a suitable transaction. For example, a transaction that verifies the SNARK proof and then issues a payment. If Bitcoin were Turing complete, you could do that in a fully automated way. In this case, the failure mode is more gracious. If you could corrupt Zerocash, then you could empty the escrow pool and therefore deprive Zerocash holders of their money. But the damage would be capped at the value of the escrow pool, and it wouldn't cause any further damage to the Bitcoin economy. It will go up in a few days, yes.
On the Skipper Cloud site?
Yeah.
The transaction confirmation process, I understand it's really short, but is the computation required for that? Is that a possible target for ASIC development, or is that more of a general computing?
So transaction requirement certainly should be done by the recipient of a payment to make sure that the payment is legitimate. Moreover, in the distributed ledger protocol, everybody checks transactions. When you construct a block, you check transaction. When you propagate, you check transactions to make sure that junk doesn't float around and get embedded into the blockchain. So actually, that's why we did that benchmark on EC2 to make sure that the dynamics of this propagation don't have any pathological failure mode because of a few milliseconds worth of delay.
I was just looking at this slide now. Is the serial number still needed?
The serial number, what is it? The serial number will be used in the zero knowledge proof and in the revealed transactions. So the serial number must be exposed when the coin is consumed, because this is what marks the coin as having been consumed, and therefore prevents double spending.
Okay. Can you just use V, P, R prime, R double prime, and APK?
I'm sorry?
Can those 5 values just be used instead of the serial number?
Which values do you propose?
Like V, P, R prime,
So,
R.
okay, let's start with V. You don't want to reveal V. When you do a pool, you don't want to reveal the values of the coin that were consumed or created, therefore you don't want to reveal V.
Okay. What was the previous, what is this, previous slide? What do I broadcast when I'm paying you? Which numbers, which values do I tell you?
So when you pay someone, you don't.
Nothing, I think, is a big deal. Nothing is.
So okay, it depends on which mechanism you use. If you use the out-of-band version, where you just send these values on some external channel, then you don't broadcast anything except these values. Of course, you did have to create this coin using a pool operation, and that broadcasts some associated values, in particular the coin commitment of this new coin. If you use the baked-in crypto, then you still don't need to send anything in addition for the send. Sorry, in addition, you don't have to send anything in addition to the transaction created by the pool operation, because in that case, the secret values will be encrypted to the public key owned by the recipient, and they'll be able to decode them there. So these are the ciphertexts. That's why they're here. This is the pool transaction that created the coin with this coin commitment, and here's the ciphertext that allows the recipient of the coin to use it.
I guess the thing is, the recipient is the one that does more of the verification. Is that right? It's like in the early on, right? You always announce that, hey, I can provide these values, and people can check if those values match.
Yeah.
Now people are not really checking values. The recipient is the main one.
So the recipient checks the. Okay, everybody checks the transactions for the validity. The recipient, moreover, checks a few other easy properties related to the content of the ciphertext. First, it checks whether he can decrypt this ciphertext, that is, whether it's really addressed to him. And if so, then he checks the internal consistency between the public coin commitment and all the things that were encrypted in the ciphertext, which could be junk. He has to make sure they're not. This is a very easy check.
Okay, any last question? I think we could keep going for a long time here, but I think we're gonna stop it here. Any last question? So I think that it's a wonderful technology. It's a privilege to have you here. It's a privilege to have